What is up, AP Chem? Today, we are going to be continuing with the neutralization process, kind of, when we talk about the hydrolysis of different salts. So this, I would say, is a more complicated extension of the neutralization process, but also sometimes not. So we'll kind of dig into this. And this is something I'm pretty confident we'll probably have to talk a little bit more about in class, but this is the general gist of what the heck is going on. So first of all, what the heck is hydrolysis? Hydrolysis is the natural tendency for some ions to react with water. So when you put them into water, some things naturally are going to react with them either as an acid or base and change the pH of that solution. So even if you don't identify it as an acid or a base, it can make a solution acidic or basic. So there are two kind of big things that happen or that are consequences of this. One of them is when you neutralize an acid or a base, it doesn't necessarily mean that the pH, when they're perfectly neutralized and canceled out, is a 7. And that's something we kind of assume. We're like, oh, well, if we neutralize the acid and the base and there's nothing left but water in that salt, it must be pH 7 neutral. No, unfortunately, sometimes the stuff that's left over, that salt, will actually cause the pH to be slightly acidic or slightly basic based on what's going on with it. And like I said, there's some substances that are naturally acidic or basic, even if they don't initially appear to be that way. So you might look at it and be like, oh, I don't know, base, I got nothing. We can take a look at that formula and try to figure it out. Now, I'm not going to cover every single possible instance, but I'm going to give you the basics here and we'll kind of talk about it. So how do I know what that salt is going to do? If you are given the reactants and you know what they are, what you can do is you can look at the salt and figure out what's going on. The easiest way is if they give you the reactants, and we'll start doing practice with that, and then we'll go into a harder situation where you don't have them. The most important thing is to look at the ions that are in the salt. And this is if you don't have the reactants. If you have the reactants, it's a little bit easier. So here's the deal. If it comes from, in your salt, the ion comes from a strong acid or a strong base, that ion will be neutral and it will not do anything when you put it into water. And we'll talk about why when we get that far. If it comes from a weak acid, that ion will be basic. And if it comes from a weak base, that ion will be acidic. Okay? So it's the opposite of what it is, the salt. So if your acid is weak, then your salt is going to be basic. And if your base is weak, it will be an acidic salt. So it's just kind of the opposite. And like I said, I'll explain why in just a minute. So here's our first example. And I'm going to start off with reactants so we can kind of work our way through this. So here's HI and NaOH. If we know our information, and these are the same equations we used from the last video. So if you want to go back and figure out where all this is coming from, you can look back at the previous sections video. But HI is a strong acid. NaOH is a strong base. And so when you think about it, H2O obviously is going to be neutral because it has a pH of 7, but the NaI is what we're going to take a look at to see if it's going to do anything funky with water. So will it react with this water that I produce or the water that's in that beaker in the first place? And here's the deal. The Na, hopefully you recognize, comes from NaOH, the strong base. That Na is not going to want to reattach with anything associated with the water because it naturally fell away from that OH in the first place. It's strong. It's not going to want to reconnect with anything. It's pretty happy just hanging out by itself. And the same thing happens with I. The I minus ion does not want to be stuck to hydrogen. They naturally go and fall apart and ionize 100%. So it's not going to want to go back and stick with anything else. It's happy flying solo. And so what ends up happening is if I mix together a strong acid and a strong base, their salt is neutral. So they are perfectly neutral if you get the exact equal numbers of moles in there, and you should have a salt that has a pH of 7. It should not affect the pH at all when you neutralize them. So you're not going to have any kind of weird leftover back reaction happening if it's strong acid, strong base together. They always have a neutral salt, pH 7, move on. Okay. Of course, that's, the easy one. We start easy. So this is the reaction that we talked about where it's hydrofluoric acid and calcium hydroxide. And they make water and calcium fluoride. And you look at that and you're like, I don't know, that looks like a salt. What's the pH going to be? So if you think about the two things that are coming together to make it, HF is a weak acid. Calcium hydroxide is a strong base. So they're going to make water, like we talked about. And then this calcium fluoride here, that's what we got to kind of figure out here. So calcium ions are neutral, and that's because they come from that strong base. They are not going to want to reconnect with a hydroxide or anything like that. They're not going to want to react with water. They don't do anything. So the calcium ion is a neutral ion. However, the fluoride ion, F minus, that's in that salt, that F minus ion itself is a weak base. So if you remember, HF would be the acid, F minus is the conjugate base. And that conjugate base has a number that makes it sometimes want to react with water. And if you're by number, I mean, if you remember our Ka values, when we talk about our strong acids, they have Kas that are super duper large. So their conjugates, Kbs, are incredibly tiny. In the case of something that's weak, it's not the case. So HF might have a decently sized K, but it still has a competitive Kb for its F minus. And what ends up happening is the F minus reacts with water and makes this a basic salt. So the calcium does nothing, but the base F minus, that fluoride ion, it does. That reaction is really important for you to know. And it's that F minus getting together with water, and it literally makes the HF again. But that's not what's affecting our pH. When it makes that little bit of HF, as a consequence, it makes some OH minus, and that makes our solution a little bit basic. So if you mix together a weak acid and a perfectly molar equivalent amount of strong base, the salt that you make, that solution that you make at the end, is actually going to be just a little bit over 7 for its pH because this F minus is going through that hydrolysis process. Okay, little weird. We will hit on this again when we talk about neutralizations, when we talk about buffers and all that stuff, but this is kind of our first introduction to that. All right, the last example we're going to get into before I stop telling you what's reacting are NH3 and HCl, and they make the salt NH4Cl. And if you remember from the last time, NH3 ammonia is a weak base. HCl, oof, you should know right away, strong acid. So when we talk about these, we know that the chloride ion, because it's coming from something that's got a massive Ka, is like a terrible, terrible base, and it's not going to do anything. But the ammonia is a weak base. The conjugate here is a weak acid, and it's going to make your salt acidic. So when it neutralizes, if you have a weak base and a strong acid, it's going to be an acidic salt. And here's the reaction for that. The ammonium ion, NH4+, gets together with water, and it turns into ammonia. And in this guy here, the hydronium ion, and that makes that solution a little bit acidic. So if I mix those two things together and perfectly neutralize them, my pH is going to be just a little bit under 7 in this case. Okay? It's a little complicated. It takes a little bit of practice. So here, we're going to take 3 different substances that we have here, 3 different salts potentially, and I want you to identify if they are acidic, basic, or neutral. The walking through of this process we will go through in just a second, but I'd like you to at least attempt to do it. So take a look at the different things that are making this up, what those could belong to as far as a strong acid or a strong base, and then make your decision based on that. And if you're totally confused, we'll go over it in like 2 seconds. So pause the video, give it a try. If you're totally confused, we will talk about it in a moment, okay? All right. I know you're excited about this, so we'll get going. Alrighty, if we look at KNO3 here, what I like to do is I like to break these substances into their specific ions. So when I look at this, I think of K+, and when I think of the other ion, I think of NO3-. And then when I look at them, I think about what they could have come from for either a strong acid or a strong base, or even a weak acid or a weak base. So when I look at this positive ion here means that it lost something to make water that was negative. And so in this case, this must have come from KOH. So hopefully that makes sense to you, because this is my salt. In theory, the other thing that was made was a water. So if I have K plus, that means that the OH minus must have, been there. So KOH is the parent for the potassium ion. And in this case, the NO3, the parent was the HNO3. So when I look at those two things and I find the parents as KOH, that's a strong base. HNO3 is a strong acid. And I know that if I mix a strong acid and a strong base together, I'm going to have a neutral salt. So KNO3 is neutral. Okay? All right. So let's look at this whole thing here. Now this is a little more complicated because the formula is kind of nasty. But if I look here, I can kind of see this Br hanging out by itself, and that's probably just going to have a -1 charge, which lets me think that this whole thing here has a +1 charge. Okay, so realistically, I have C5H5, and oops, nope, I screwed this up. Hold on. The formula on this should be C5H5NH. My bad. Nothing changes from this process though. So this is a +1, this is a -1. Sorry to let you down. So anyways, it's C5H5NH plus. And then this guy here is Br. Getting ahead of myself here. All right, so the Br minus, that one's easy because it comes from HBr. Guys, I'm really struggling on this one. Okay, HBr here is definitely a strong acid. This nonsense right here, though, that's a little more complicated. So if I look at that, it's probably got to be the base, and it's definitely not one of my strong bases, like at all. So even if I'm not 100% sure about where this thing is coming from, I know that this thing is probably parented by a weak base. And if that's the case, we just lose an H. So it's going to be C5H5N here. And if I have a weak base and a strong acid, what's going to end up happening is I'm going to have an acidic salt. Okay, and just as a little bit of practice, I think it might be a good idea for us to try and write that equation. So my ion here from the salt, okay, if I get that together with water, and I know that this is going to be an acid because it's coming from a weak base, we'll get together, and now this is an equilibrium process. That's going to make C5H5N and H3O plus. And if you don't feel 100% confident about this yet, that's okay. We will do a lot of practice. All right, last one. Who is the person who picked these? All right, so if I look for a natural, easy thing to find in here, I see Na. That's a +1. That means that probably all of this nonsense here is going to be a -1. So when I think about what must have made this, if I think about neutralizing, okay, Na comes from NaOH, and that's a strong base. And then this whole thing here, CH3, CH2, COO minus, that, I don't recognize it necessarily right off the top of my head, but that also means it's not a strong acid. So this parent is probably this guy here, CH3, CH2, COO. H. I just add a hydrogen on there. And that is a weak acid. Okay. So if I think about how this salt was formed, it was formed from a strong base and a weak acid mixing together. So that means that this ion that's floating around in my salt is a weak base. And so it's going to make a basic salt. Okay. When that goes into water, CH3, CH2, COO minus. When that thing gets together with the water that's produced, as well as the water that's already in solution, that is going to make its parent acid, CH3, CH2, COOH, and OH minus. So it's going to take the H from H2O and it's going to make this OH minus, which makes your solution basic. This is complicated and takes some practice. So you can bet your booty that we are going to be doing a lot of practice with this in class along with our neutralizations. So if you have any questions, please, please, please make sure you get those things cleared up. Otherwise, really, you're going to need it. Good luck.